So in this section of the course on measure theory, which is the rest of the course, we will look into some of the early chapters of our textbook, and we'll probably not, with what we have, like half a quarter, we will probably not do anything like a complete course in measure theory, but hopefully it gets you started on a journey that you can continue after the course if you want to, or at least it gives you a look at what there is that could be learned about. So a lot of the notation that we're setting up in our new textbook is going to be the same notation that we've been using, assuming naive set theory with the axiom of choice. But here's one bit of notation that I noticed that looked different and actually looks pretty nice and convenient. If you have a sequence of sets, like A sub n, then when we write A sub n up arrow A, what that means is that A sub 1 is contained in A sub 2, etc., like this, and that they limit to A in some sense, but not in the sense of real analysis limits, rather in the sense of set theory. So if you union all of them, then you get A. And this is the intersection version. So this one is saying if you have nested sets like this, so a shrinking sequence of sets, then this notation says that they shrink down to become exactly A. So that means if you intersect all of them, then you get A. So that's just a nice notation. So if you remember the nested interval property, of R, we now have a nice way of saying it using this notation. It says that if In is a sequence of intervals, actually a sequence of non-empty closed intervals, such that this is actually a nested sequence and their intersection is some set I, then I is non-empty. Okay, so nothing new there. I just want to get practice with this nice notation. So our main concern is with, in measure theory, is with the idea of measure, which stands for sort of length or area or volume, etc., of sets. So we want a way of measuring the size of a set. And cardinality won't do. So cardinality is one way of measuring the size of a set by just describing what are the elements, but we're not really talking about cardinality here. So, for example, the closed interval 0 to 1, we'd like a framework in which we could say things like this has length 1, or whatever length we want to assign it. And cardinality does not provide such a framework. As far as cardinality is concerned, this set and this set have the same cardinality, right? They both have the same cardinality as the cardinality of R. So we want a way of measuring length in the same sense of length that you think of when you think of this set having length 1 and this set having length 2. And it doesn't necessarily have to be it doesn't really have to be measurement of subsets of physical space. So, a space in mathematics can be used to represent more than just a physical space. So, if it were a physical space, then the sizes of sets might be lengths for a one-dimensional space or areas for a two-dimensional space or something like that. But a space in mathematics can be like a space where the points represent different things, like maybe events, and then the sizes of sets could be probabilities of batches of events. Or one could use the sizes of sets to represent, rather than volume, they could use it to measure something else, like mass, and have the way in which you measure sizes of sets somehow be a way of representing a density of something. So we start with this idea of measuring length, area, or volume of sets, but eventually it'll be so general that it really can be used to talk about a lot of different things that are not so much about physical space. So suppose we want to talk about measuring the sizes of subsets of the real line. Then what kind of thing would we want? We would want some kind of function from the power set of the reals, so the set of subsets of the reals, to the reals. A function of this type, maybe. So this is just this is not actually how we're going to develop things. This idea does not work, but this is what you might first think. Like, I want some function that assigns to any given set of real numbers a specific real number which is the size of that set. Then if you had such a function, you might call that a measure, a way of measuring lengths of sets. And then you might hope that it does certain things, like you might hope that the unit interval gets sent to the number 1, meaning that it has length 1, and that maybe it doesn't matter if you include the endpoints, that should still have length 1, and interval of length 2 should have length 2. So there are certain ideas you have about what you wanted to do to certain sets, but you hope that you can extend those ideas in some way to a large collection of sets, like maybe all of them. Well, it turns out that if you try to get all of them, then something's going to break down somewhere. It's going to end up not being a sensible way to measure sizes of sets. So there are a couple of things we need to get into to flesh out this conversation. So one thing we need to do is decide how it is that we are going to get this mapping to work. How do we measure the size of a set? And the other thing is, if this doesn't work, which it's going to end up not working, then what will? So what will be the collection of sets that are measurable? What will be the collection of sets for which whatever we come up with here ends up making sense? So these two components of our discussion are going to be, this one is called measure. So when you figure out how to define a function here that measures the size of a set, that function is called a measure. And then this component of our discussion is going to be called a sigma algebra. And we will officially define that soon. So these are the two things we study. And you might expect that we're going to start by studying measure and then see what the domain of a measure ought to be. But no, it actually makes more sense in the end to first figure out what sigma algebras can be in the abstract. So it's going to be a pretty abstract discussion of sigma algebras to start with no measure put in necessarily. Then we'll introduce measures. So our first discussion is going to be about what kinds of collections of sets does it make sense to talk about measuring the sizes of. And here I was talking about measuring sizes of subsets of the reals, but in general, it doesn't have to be the reals here. You could put any set X here and talk about, in general, how to measure the sizes of subsets of X. So that's where our first initial discussion will be about abstract, measurable sets.